Well, stats people, we have done it. We've arrived at the very last day of Chapter 9. And today for Chapter 9, we're going to be looking at something called Statistical Power. Now, statistical power is actually related to those beta calculations that we were talking about way back, and I think it's 9.1, Section 1, where the probability of making a type 2 error was beta. Now, beta is also used for this thing called power, and before I say too much, let's go ahead and take a look at it. So the mean score on the math portion of the SAT is 511, with a standard deviation of 120. So we believe that students at Taft High School have a higher mean than the national average. I mean, of course we do. To find out, we're going to take a random sample of 8 students and find their average. And then we're going to use that data to conduct a significance test at the 5% level. So far, this just sounds like exactly what we did in the last section with 9.3. Day 1, the significance test for mu. So ho-hum, the first thing we're going to do is write the appropriate hypotheses for the significance test and define the parameter of interest. So we can say that mu is the true mean math score for Taft High School. For our hypotheses, we have H naught, mu is equal to 511, and H alternative, mu is greater than 511, because we believe that students at Taft High School have a higher mean. Now, this is just going to be hypothetical. Let's hypothetically suppose that the mean math SAT score at Taft High School is 535. We don't know where that number came from, but usually that comes from some sort of testing. Okay, so yeah, we're going to call that our alternative mu. 535 is the alternative mu. Go to statlet.com, launch the Statistical Power applet, and then enter all the information into the fields, and you'll notice a value called power. Okay, this is a probability that the significance test will find convincing evidence against the null you've entered. So before we get too far into that, here is that applet. And let's fill in all of our information. We know that mu was 511. Our alternative hypothesis is mu is greater than 511. Our standard deviation, what was that, 120? Yeah, it was 120. And our sample size was 8. Alpha level, that looks correct, 0.05. And the alternative mu was 535. So let's update that. There we go. 535. And here are the 2 different curves that, could be. Now, this first curve over here is going to be the curve where 511 is the mean. Let's go ahead and copy and paste this so I can notate. So the first thing we're going to notice is the curve on top has the mean of 511, and that is from our alternative hypothesis. The next thing to notice is that our alpha level was 0.05, so the orange area here, this one right here, that has an area of 0.05. Now, remember that we're not sure if this is the actual curve for mu. We're making the assumption that mu is 511. And if we assume that mu is 511, that means this area over here, this rejection region, that lines up to any value of x bar, which is, and I think this is around 580 if I did my calculations correct. You don't need to worry about how to do that calculation, although you certainly could. This is just an inverse norm calculation with the area up here being 5%. Now, what we're going to do is say that, okay, let's pretend that this isn't the curve. Let's pretend that the actual curve is this one down here. This is our mu alternative. So let's pretend, unknown to us, the actual mu, the mu alternative, is 535. Okay, if that's 535, then remember that we're going to reject any x bar greater than 580. So where does 580 line up on the mu alternative curve? Well, on the mu alternative curve, that 580 lines up over here, and that has its own z-score as well. And we can see that this area right here in red, that's the area of, if 535 was the actual mean, that area, the red area, would be the actual probability that we're going to reject the null hypothesis. So this area here is what we call power. And by definition, power is at 1 minus beta. And we just calculated power to be 0.140. The calculation of power is a z-score calculation. And the only thing that changes is we're using a different value of mu. Instead of using 511, we use 535. So there's no real easy way to tell you how to calculate this beta. And that's actually not something you're going to have to calculate on your own. It will, on the AP test, they'll just tell you what the power is, or they'll tell you what beta is. If they tell you what the power is, then you say that's the probability of rejecting the null hypothesis. Because if we reject this area over here in red, corresponds to the rejection region in the null hypothesis. They correspond with each other, so they are the same thing interpretation-wise. So power is the probability of rejecting the null hypothesis if the mean was actually 535. Now the other side of this area in white, that's actually beta. The other side of this curve is beta. And beta is the probability of not rejecting the null hypothesis if the mean was really the alternative mean. So there's a lot of little calculations that you need in order to make all of this work. I don't want you to think that they're difficult. They're not difficult, but your head needs to be very flexible in thinking about alternatives and what if. So in terms of the AP test, yet again, you're not really going to have to calculate beta, but you will have to know how to interpret beta. So power is 1.4, which is the probability of rejecting the null hypothesis if the mean was actually 535. Let's interpret this in context. If the mean SAT score at Taft High School was actually 535, there is a 14% probability of correctly supporting the alternative hypothesis. Simply put, power is the probability of making a good decision. That decision is rejecting the null hypothesis. So let's move on here to our question 3. We want to increase the power of the test. How could we adjust each of the following factors to increase our test? We're going to use the applet to explore each one of these. So let's start with sample size. What happens if I increase sample size? Let's say I go to 40. Is that going to increase power or decrease power? Looks like I increased power all the way to 352. 352.352. Let's reset things. Let's put this back to a sample size of 8. And let's change our alpha. Let's make our alpha 0.1. And it looks like power increased as well. How about if I make that 0.2? Yeah. Alpha, if I increase alpha, I increase the power. And that should kind of make sense, because if I increase alpha, I decrease beta, which means I also increase power. So, that's a lot of logic to kind of go through. If I increase alpha, I decrease beta, which means I increase power. Okay, the last thing is, what if I consider an alternative hypothesis that is, let's say, greater? So let's go to let's go to 600. What'll that do to the power? Oh, that's going to increase power. So if I consider a alternative hypothesis that's further away from the mean, then I'm going to increase power. And I imagine if I go closer to the mean, let's say we go to 520. If I go to 520, if I move closer to the mean, that should decrease the power. And yeah, it does. So here's a summary of what we just found out. An increased sample size will increase power. If you increase alpha, you're also going to increase power. And if you consider a more extreme alternative mu, then you will also increase power. This brings us to the important ideas for today. So we have the power sentence frame, and the sentence frame is assuming that the parameter and context is alternative parameter value, then there is a power % probability of finding convincing evidence for the alternative hypothesis, H alternative. Now, over here, we have kind of a truth table. I guess that's what some people call this, but a lot of people are really into this table. So we'll notice that if we have the reality of the situation on the columns and the test results on the rows. So let's say that we reject the null hypothesis, putting us in the first row, and the null hypothesis was actually true. Well, that means we made a type 1 error, and that probability is alpha. Likewise, let's say I fail to reject the null hypothesis, and the null hypothesis was actually true. That means that you actually made a correct decision by failing to reject the null hypothesis. And this brings us down to the last check your understanding here. We've got, can a 6-month exercise program increase total body bone mineral content, TBBMC, of young women? A team of researchers is planning to study this question. The researchers would like to perform a test where H0 is equal to 0 and H alternative equals mu greater than 0, where mu is the true mean percentage change in TBBMC during the exercise program. The power of the test to detect a mean increase in TBBMC of 1% using alpha is 0.5 and n equals 25 is 0.8. So let's interpret that value. First thing we do is copy our sentence frame. Next thing we have here is parameter and context. So our parameter is the true mean change in TBBMC. Assuming the true mean increase in TBBMC is 1%, then there is, what was my power? 0.8, so 80%. 80% probability for finding convincing evidence for the alternative. The mean TBBMC increase is greater than 0. Okay, so it's a probability of making the correct decision if the true mean TBBMC is 1%. So let's find the probability of making a type 1 error and a probability of making a type 2 error. The probability of making a type 1 error is the same thing as alpha, and we're told that alpha is 0.05 right over here. Now the probability of making a type 2 error, well, that's equal to beta. And beta is 1 minus power. So that's 20%. Let's look at question 3 then. Determine if each of the following changes will increase or decrease power and explain your answer. So if we use alpha of 0.01, that means we're going to decrease alpha. So that should decrease the power. And interesting, something to think about is decreased alpha will decrease power since we're less likely to reject H naught. And rejecting H naught is a good decision in this case. So decrease alpha will decrease power. What if we use n equals 100 instead of n equals 25? Increased n will increase power since we are more likely to detect differences in the parameter. You'll think all the way back to, I think it was chapter 4, where we all got kind of crazy with increased sample sizes. You know, and one of the stock answers here were increasing the sample size will enable us to detect a difference. And this is what we're talking about. Increased sample size allows us to detect a difference. In other words, allows us to reject the null hypothesis. So, or fail to reject the null hypothesis. So yeah, increased n will also increase power. So that's it for our chapter 9, actually. We're done. Now, the power thing that we are talking about, I know it comes last in this chapter, but I want to assure you that this isn't the major part of this chapter. If you can do your significance test for P and your significance test for mu, if you know those really well, then you're going to do really well on this chapter. Power, that's just a little bit extra to get you from wherever you were, just to get you to the very top level. So that said, good luck on your chapter 9 test, and we'll see you very next time we meet.